Welcome to my channel. Today we will study magnetic force. Just like the fields of two interacting magnets, the magnetic field due to current in a wire interacts with an external magnetic field due to permanent magnet and give rise to a force on the conductor. Kindly note that force is produced as a result of interaction of two magnetic fields when they combine and interact with each other. The magnetic field due to magnets will be uniform, as we will see in our next slide. As force is a vector quantity, so we will find out its magnitude and the direction as well. Force on current carrying conductor in a magnetic field. Now consider a current carrying conductor of length AB. It is an aluminum rod and it is placed in the magnetic field of a permanent magnet. See, the field is uniform. Now this rod freely rolls along the two horizontal copper rails as soon as the current in it is switched on. Now what happens when the current is switched on? As we have studied in our last video, there will be a magnetic field due to this current carrying wire. Those who have missed the last lesson, I would recommend to go through it, as I have given the link in the description as well. Now what happens? Due to the interaction of two magnetic fields, one due to current carrying conductor and other due to permanent magnet, gives rise a force on this conductor. As force is a vector quantity, now we will find out how it depends on various factors, and we will find out its direction as well, which will be due to Fleming's left hand motor rule. As I have already told that magnetic force of magnet and magnetic force of current carrying conductor, their combined effect give rise to this force. Okay, so this force is used in electric motor, so the production of this force is known as the motor effect. Now please note that if we reverse the direction of the magnetic field, the direction of force on the conductor will also be reversed. Now let's see what are the three factors on which this force depends. This force depends upon three factors: magnetic flux density, which is measured in Tesla. Units of flux density are Tesla. Number two, length of the conductor, and number three, current through this conductor. Now obviously we have seen that these three factors like force, current and magnetic field, these three are mutually perpendicular to each other. And we will also see in the next slides how this force depends upon angle theta as well, which is the angle between magnetic field lines and current. We know that maximum value of sine theta is 1 when theta will be 90 degree, and sine 0 is 0, which is the minimum value. When theta is 0, sine will have 0 value, and then force, it becomes B L I sine theta, and this theta is the angle between field lines and current through the conductor. So it varies, it depends what is the angle between current and flux density. I will clarify it further here in this graph. As an example, if we plot a graph between force and current, then it is a straight line. It means this magnetic force depends upon the current and it is directly proportional. If current will be more in the conductor, force will be more. And if we increase the length of the conductor, so force on the conductor will also increase, so the graph will be again a straight line. Now the third factor, magnetic field, magnetic flux density or magnetic field lines. See, the direction of the field lines is from left to right, and current through the conductors are given at various angles. As an example, if current through the conductor is at right angle to the field line, so angle theta will be 90 degree and sine 90 will be 1. So it will be the maximum value of force when field lines and current are at right angle to each other. And for other values of theta, force will have different value. And see this last, when theta is 0, sine 0 will be 0. So there will be no force acting on the conductor if current passing through it is parallel to the field lines. So this is what I tried to explain here already, that maximum value of theta is 90, so force will be maximum. It will be equal to BLI. And when theta will be 0, this factor will be 0. So force will be 0 in that case. Now Fleming's left-hand rule. Fleming's left-hand rule is used to find out the direction of the force on the current carrying conductor. Now the three things, the magnetic field, the current in the rod and the force on the rod, these three are mutually perpendicular to each other. These can be represented by holding the thumb and the first two fingers of your hand in such a way that they are mutually at right angle to each other. All these three are at right angle to each other. Then if thumb indicates the direction of motion, first finger indicates the direction of external magnetic field, then second finger will indicate direction of conventional current. Now if the thumb and the first two fingers of the left hand are held at right angle to one another, with the first finger pointing in the direction of field and second finger in the direction of current, then the thumb points in the direction of force or motion. Now let's take an example. These green lines indicate magnetic field and this purple line shows different directions of current through this field. And we have to investigate whether there will be a force acting on this conductor or no in these three cases, A, B and C. Let's take the first case. As I have told so many times that three quantities, field lines, current and force, are mutually perpendicular to each other. So obviously, and we have studied already angle theta in terms of angle theta also, that if angle theta is 0, sine 0 will be 0. So there will be no current, no force acting on the current carrying conductor if current is flowing in the same direction in which these are the magnetic field lines are going. So force will be 0 here. In second case, as current is at right angle to the field line, so we will have maximum value of the force acting on the conductor, as angle between I and B, the field lines, will be 90 degree. And so direction of force will be, according to Fleming's left hand rule, it will be into the plane of the paper. And in the third case, force will be down the page. Thank you for watching, and please like, subscribe and share my channel and press the bell icon to get notified of my latest videos.